After the Zwift cheating video, several people started suggesting the novel idea that why don't we just weigh at the trainer? And that would allow you to do things like weigh continuously, so you have less of a possibility of actually cheating. Initially, I'm kind of dismissive of the idea because, quite simply, your weight isn't just on the trainer. It's partially on the front wheel. But why can't we just weigh at the trainer and the front wheel? So we did that. Any hardware hacker kind of hits that problem every now and then where they need a part or a board or something that will do a certain task. And normally you go online and you try and find something. And in some cases, you just find garbage. I mean, like not literal garbage, just something that is ill-suited for the task. So I designed and built an analog to digital converter board for an Arduino or development kit that would allow me to better interface with strain gauges, something I do kind of on a regular basis, and there's nothing out there off the shelf. So I needed to make something. So this here is actually an ideal showcase for what I had developed. Essentially, I was going to have at least potentially 2, but possibly 5 or even 8 inputs, depending on how I wanted to build this. So here's the basics of the whole setup. Essentially, we've got a full weight scale out front that we've just tapped into the existing strain gauge setup, no modification. In fact, if I put batteries back in it, it still works as a weight scale. The other 2, well, technically 4, the other 4 feet are actually the 4 feet from an existing scale, just mounted to small blocks of wood so that they can distribute the forces in one specific point. So there's actually 2 under the rear and 1 on each extended leg. All of these analog signals run back to an analog to digital converter, is plugged into an Arduino, but I could have just used my NRF52. However, for this demo and the amount of time I want to spend on it, I really wasn't that useful. So there's 5 outputs here, the blue being the front wheel, so that's just the weight scale under the wheel. The red and the green are the front legs. You can see the green actuate there for the front right. The yellow and magenta are in the rear, and the red is the front left. Now you should be able to see as I get on the bike now that the left is going to peak a little higher as I clip in on my left side. And about the same, but it's hard to really tell. I mean, there's such an offset. So as I just sat there, the weight will look fairly stable. There's what looks like noise, and a little bit of it is noise, but a lot of it is just little micro shifts of my weight. And as I changed hand positions, you'll see that that front wheel took more of the balance. The blue is actually moving opposite, so the 4 trainer sensors, they go higher as the load increases. The blue goes lower as the load increases. So I changed hand positions and there was very little shift in balance. It's not perfectly detectable. But as I'm pedaling now, you can see some cyclic stuff going on. And there's a little bit on the front, that's kind of this bounce going on. But at the left and right legs, the far legs in the red and the green, what we're seeing is very large cyclic data. And if we zoomed in, it's actually opposite to each other. So as the left increases, the right decreases and vice versa. So that cyclic nature is still there and it relates to my cadence. It's actually in sync with my cadence. So as I'm shifting positions now, you saw that when I went back on the seat, the load shifted more to the trainer and decreased, so the blue went up. And now I'm getting ready for a sprint and you'll see that the balance shifts a little bit more again. The trainer weight decreases, the front wheel weight increases. As I shift back, you'll see that goes back to normal. But if I kind of maintain my front balance over that without touching the bars, the front rear balance isn't that effective. So I'm kind of pinching that seat or just trying to prevent myself from rotating forward. So you don't actually have to be touching the handlebars to show that balance. And you can see as I get off, the data is all kind of coming back into line where it was. The results of this have been astonishingly positive. With only a few seconds of filtering in order to remove some of that harmonic from the cadence and the pedaling, there is very little error here. On the screen right now shows a slightly filtered graph, and by filtering, it's a simple rolling average for about 5 seconds. When we actually look at the amount of error against my weigh-in prior to getting on the bike, it is actually well below 1%. You'll see a little bit of drift, and that's likely temperature related. As I ride the bike, the room is heating up, and these gauges are not thermally compensated. So that can be further improved. So we're actually getting down to 0.5, 0.3% error. The other interesting aspect of this is actually related to the fore aft balance. So not only am I able to kind of figure out when my hands are on the handlebars, but to a certain extent I can actually tell when I'm sprinting because the balance tends to move a little further forward. Some sprinters may not, but in the case of myself where I raise myself forward to get more torque down onto those cranks, I can easily detect that. Hand position, I'm not so good at detecting as I explained earlier, but there is a subtle difference between some of these. I was quite surprised at the quality of the solution, not only the accuracy, but the ease of implementation. It took very little to actually build and calibrate all of this equipment, especially with having the specialized analog to digital board that I had already developed. Not only that, there was a lot of potential for anti-cheat that can come out of this, such as the continuous weighing as the first step, but even things like synchronizing the weight felt on different feet with the cadence. That provides a very strong mechanism for a very hard to defeat anti-cheating mechanism. Not only that, there are some interesting metrics such as when you're on your handlebars, potentially maybe where you're holding on the bars, but it's a little difficult right now to figure that out. But when, if you're sprinting, if you get up and you're like me, you hold onto the bars and you move yourself forward, you're going to be easily able to detect that with the weight transfer. So lots of really cool things can definitely come out of this, especially with a very, very low cost implementation. If you're here primarily for the Zwift stuff, that's all I really got for you. Thanks for watching. Please like or subscribe. It certainly help the channel improve the popularity a little bit and allow me to keep making some of these videos. And if you're here for the hardware hacking side, a few more minutes I'll talk about some of the electronics and the choices and the disassembly of all of this equipment so that you can see and understand a little bit better. Thank you. Let's tear down the scale. This is the simplest component, so it should be the easiest to figure out. So inside, we have all these little feet with wires ran back to this main circuit board. As you can see here, they've labeled everything nicely for me. That was a -S, and moved some of these wires out of the way. We should see a +S here. So those are two differential signals. Back in this area, there's, you can almost see it, a little E-, so that's the negative excitation. And there's one there that's labeled the positive excitation. The feet are extracted from a different scale, so you can see that here. And what you'll notice is that the width of those little legs compared to the center are almost identical. And they have these large overhangs here that are to increase the stiffness so that they don't bend so much, whereas these other sides that are supporting the weight are also identical in dimension almost. And if you look very closely in here, you can kind of see, hold on, if I flip it over, you can kind of see that there's a strain gauge, and it's likely a contraflecture type strain gauge arrangement, very common for those type of very basic and cheap load cells. So you can see it in there, and that's
kind of just a direction that it kind of cantilevers on, and you put the cap back on and it's pretty much ready to go. So this here is the Breakout board with the heart, the ADS 1248. So this is one without so many things wired to it. And there's a lot of different I/O from this chip. But first thing is we've got a voltage divider here. I need that for the half bridge. But the primary inputs are this row here. And we have a VREF, the ref positive, the A in 0. And we have A in 1, ref negative, and the VREF common. Those are these three here. And those are our inputs. Those two are our references, and those are what supply it for our string gauge setups. So we're using a simplified setup, and this row here, kind of in the same vein, but it's using a current exciter as the source, and same inputs in the middle, refs on outside that, and the power supplies outside that. This row here, exciter and ground, but it's just primarily a row of 4 other inputs.
The board is designed for a 6-wire string gauge configuration because a 6-wire setup is actually the most precise Wheatstone bridge. So in our case, we have a Wheatstone bridge here, and we're going to power it from the reference, the 2.048 volt reference, and the power then returns, or the current returns back to ground through this wire. But because there can be voltage drops in these wires, we sense the voltage at the bridge and we bring them back to the reference input. So this is using an external reference input. We could do a multitude of things here, such as driving current or just an analog voltage somewhere else, such as a battery directly through a FET or something. But the 6-wire configuration, by pulling our own references, it allows us to get a better reference on the bridge and gives us more accurate signals here. So we can reduce this down to a standard 4-wire configuration by having our Wheatstone bridge, and our references just tie back. Our positive and our negative reference ties back to our VREF and our VREF common, which in our case here is ground. It doesn't have to be, but that's a whole other thing. So this has a few pitfalls, namely longer cable runs causes desensitization of the bridge. So when you put 100 kilos on it with a short run of wire, it's going to give a different response than if you have a long run of wires and put the same weight on it. So you have to either calibrate that out, which is fine, but the bigger pitfall is you might have temperature variation that is actually caused by the wire, so you have to keep the wires identical in length. This is almost, but not quite what we see in the scale. The scale will actually have 8 gauges. I've erased all the electrical connections so that we can talk about those load cell feet. They're kind of a dumb load cell, but they're worth talking about. So they kind of have some interlace feet. So when we push on those, the center beam actually bends in this S shape. And that S shape actually means that there is an area with tension and compression, and then on the opposite side, compression and tension. This means it's ideal to put a half bridge, Wheatstone bridge, so essentially half of what we had before. And they take 4 of them and they combine it into one Wheatstone bridge. But that has 8 gauges, not 4. So this is wired as a half bridge configuration. And if we just look at one of these zones, it's the exact same. So it's a tension side and a compression side. In order to get a signal out of a Wheatstone bridge, we have to electrically imbalance. So essentially this side and this side each act as a voltage divider. So we should have 0 volts when we measure differentially to those points. So we want one to drop and one to raise, or vice versa. So in order to do that, you want to have all your tensions on one quadrant, and diagonal to that, you want to have also your tension, your compressions and compressions on the other diagonals. This means that they're all working together. So even if I press one foot, it's going to unbalance the Wheatstone bridge, or another, or another, or another. The idea is that in unison, they work together. But this is also one of their kind of pitfalls to this design, is that mechanically, if those dimensions are different, if the gauge is on a slight incline or angle, you can have different sensitivity at each foot. On a weight scale, it's not a big deal, but this is actually the identical setup that is used in a lot of spider-based power meters, such as, the gold standard. So mechanically, we want these to be exactly perfect. In reality, they're stamped steel, and they're not that perfect. So there's a little bit of difference in their sensitivities. But because things are different on the back of the trainer, I wanted to wire it differently. So you heard me mention that these are half bridges. These individual feet are half bridges. We can wire and use them in a different way. So front weight scale, we're using a 4-wire, we know it's not as good, 4-wire configuration with 8 gauges all wired as one big sensor. And in the rear, we're using 4 half bridges. So I'll show you that next. The second method we have of measuring these are using half bridges. So I mentioned that each of them can contain a tension and a compression half bridge. And what we can do to make a full Wheatstone bridge is we measure that against a dummy, essentially a voltage divider with precision resistors. So in this case, we take all of our 4, and they all have their signal outputs from each foot under the trainer in the respective areas. And we have this dummy, and we have to use a differential style input. So we're measuring the voltage between this dummy and one of the half bridges. And then we just repeat that a second and a third and a fourth time. It gives us the option to either calibrate all of the feet individually, so each one gets their own calibration factor to turn their digital signal into a force, and then we can sum up all the forces, or we can digitally sum them up and then use one calibration, which is the digital equivalent of what the regular weight scale is doing by electrically connecting them all together. I tried both methods for calibration, and surprisingly they were very close. But we got to see some cool things when we measured them individually, such as when I pedal, there's a rocking motion back and forth in terms of the wider feet. You can clearly see that my cadence relates to exactly where I am, and the force and pedal stroke relates to that. So it was really neat to be able to see that, and if they were wired all together as one unit, I wouldn't be able to see that. So that's kind of how it all works. We didn't use any 6-wire configurations in this, even though I know they're superior, but we actually had really, really good performance from some of the small, medium cable runs. They're not exceedingly long cable runs, but they're longer than I usually deal with. And response was generally very good, so I think that was a bit of a win.
So most hobbyists end up using this HX711 Breakout board for their load cells and their strain gauge stuff. The reason is it has a gain stage and it's a sigma delta, which works very well with load cells. But it doesn't have a proper internal voltage generation. There's no true external voltage referencing, so you can't pull a reference at your bridge setup. And it's really low in terms of data rate configurability. The result is it's a high drift part with really, even if you can get the drift under control, effectively 12 to 14 bits noise free. It's a really poor quality part. So I used a part I'm very familiar with, the ADS 1248. It's a 3rd order sigma delta modulator. It has a precision gain stage configurable up to 128. It's generally pretty low current consumption and has a built-in precision reference that can actually supply 10 milliamps of current. In addition to that, it has dual current exciters with dedicated output pins, and there's 8 configurable differential inputs, so you can set up a wide variety of sensors. And in addition to that, you can set up different types of sensors. So you can set up something like an RTD that has a reference resistor you're flowing current through, and pull a reference from that, while you can pull a reference directly from a Wheatstone Bridge in a 6-wire strain gauge configuration. It's configurable on data rate, which is great, and its noise performance is very, very good for a fairly easy to use part. Maxim Analog Devices has parts that are lower power consumption, and even though their spec sheet shows identical noise performance, I found that their parts tended to actually have higher noise, and at similar cost, they were way less feature rich.
No, kitty, go away. Why not?